Hello everyone and welcome to my presentation today. I'm going to be talking about a HEC-HMS and HEC-RAS 2D study for rain on snow on grid with Uplands 2. It's a case study in the Sierra Valley of California. Now you're saying, why do we care about the Sierra Valley of California? Well, because it's a little bit like the west slope of Colorado, a little bit like the Front Range of Colorado, and it has significant rain on snow. So it can be of interest. It's of interest to me for sure. Anyway, Sierra Valley is 50 miles northwest of Reno, Nevada. So it's right across the border from Nevada and California, 40 miles northeast of Sacramento. It's on the leeward slope of the Sierra Nevada range, meaning it's on the inland side. The valley is surrounded by mountains. It's also surrounded by national forest. It is the headwaters. The 586 square mile watershed is the headwaters of the Middle Fork Feather River. In this basin, particularly at the valley bottom, they do have a flooding history. You can see in this photo that in January of 2017, they had some flooding. They had some road flooding for sure. And you can see that flood is pretty widespread across this whole photo. It's actually kind of a scenic photo. And it's a don't drive through the flooding waters photo too. Remember that, everyone, turn around, don't drown. But this actually wasn't the flood of record in 2017. That came later, that came in February. But you can see in the annual peak flows for the river gauge at Portola that man, those floods happen in late winter, March and February predominantly, with a couple peaks of record in November and December. So it's really a rain on snow event, late winter. Those events are driven by the Pineapple Express weather phenomena that comes all the way from Hawaii across the Pacific Ocean, basically creates an atmospheric river, driving precipitation all the way across the mountains to the leeward side. So there had been a study conducted for this watershed. It was finished in about 2012, but when the community had a chance to review it, they had some significant feedback, mostly that the rain on snow assessment did not represent the observed floods that all of the communities in this watershed, particularly Loyalton and Portola, had observed. They'd seen in action, and they hadn't even experienced the flood of record yet, or the current flood of record. The other thing that was noted was that the snow parameters were developed from SNODAS predictive data, and that those snowmelt parameters never were able to be calibrated. And the last note, given where we're at today, was that they knew that rainfall was now outdated. The original study used NOAA 2, and NOAA 14, by the time the study was completed, NOAA 14 was out. This community wanted that update as well. So basically, AECOM's work became a study of parameters. We're going to talk a lot about those parameters. We're not going to cover the basics of the hydrology or the RAS 2D. We're going to talk about the parameters we developed and how they tied together, and then how we were able to use those parameters for calibration. So let's start with the HEC-HMS parameters. So some basics, although I said we're not going to talk about basics too much, here's the basics. Uplands Hydrology, because we do have uplands and valley bottom, makes an important consideration because we need to tie them together. The Uplands Hydrology is 86 subbasins. You can see them here. Subbasins vary in size from about 0.2 square miles at the very edge of the watershed, or excuse me, the very edge of the valley bottom, up to these large watersheds above Lake Davis and this other reservoir where the entirety of the watershed basically drains the reservoir, so that's why they were not further subdivided. We did adopt the NOAA 14 rainfall, and we'll talk a little bit more about that in a minute. We did continue with initial and constant loss methods. We did use the SCS lag transform, constant base flows, temperature index methods for snowmelt. In the uplands basins, we have a couple of spots where we do have some channel routing. We have about 20 basins and 2 different locations that route together before entering the valley bottom, and those 2 reservoirs I mentioned. For valley floor hydrology, we have 3 subareas. It's very flat, but we still needed 3 subareas because of land use, soil type, and precipitation. The precipitation does, and you'll see that in a second, does vary across the valley bottom. So we wanted to make sure to account for that and develop homogeneous areas. And again, the difference here is that we have no routing at all. The routing comes in the HEC-RAS modeling. So now to get to that source data for our parameters. There are 13 gauges from the California Department of Water Resources. This is amazing data. Some of the record is beyond 50 years, up to 70 years of information. That's like the best data that I've seen in my 23-year career. It's the most data I've ever had to work with. And I have to shout out to the California Department of Water Resources for maintaining these gauges. One of the gauges you can see here, Independence Creek, that puppy's been in existence for a long time. So I was pretty excited to work on this project when I found this data, to be honest. So the first parameter that we had to look at is the rainfall. So we had the 24-hour precip from NOAA 14, and I'll note that we selected the 24-hour event based on California Department of Transportation guidance. We used Climate Region 3 in the combined quartile case. And this is the annual maxima series. But volume 6 of NOAA 14 includes numerous temporal distributions, or basically how do you distribute the rainfall over time, right? And they don't really have specific guidance on what to use where. So we pulled out the gauge data, had 24-hour precipitation events, observations at Grizzly Ridge and Sierraville, and we plotted those up over the record. And we looked at the mean, and we looked at what temporal distribution best fit that mean, and it's a little bit better at Grizzly Ridge. You can see that the heavy red line and the black dashed line are pretty dang close. Have a little bit of an anomaly on Sierraville, but still best fit was that 50% temporal distribution. So we used that to develop individual hyetographs for the frequency events for each subbasin. Area weighted rainfall, by the way. The next thing we needed to look at, like I said, there was base flow. Base flow was observed by field observations. The earlier study included base flow, so we also have that to back up that it did occur in the watershed, but they didn't document their source. So we needed to basically figure out our own. We took the Middle Fork Portola gauge, another CDWR gauge with 15-minute observations, plotted up those observations for the late winter time period, because of course that's what we care most about. That's when our floods of record occur. And you see that in this plot. And then we basically did a visual assessment, and we're like, okay, where do we see the most information on the low flow side of the range? And that is right around the 100 CFS marker. So we selected the average base flow as 100 CFS, and this is base flow at the Portola gauge. So we took that information, we calculated a unit base flow, so basically divided it by the watershed area, came up with 0.17 CFS per mile squared, and then applied that to each of our upland basins. and our valley basins. Now we get to the fun stuff, snow melt. We looked at the snow records at these 6 gauges for December through June. We wanted to figure out when is the biggest snowpack. Consistently across all of the gauges, the biggest snowpack occurs in March. Depths and snow water equivalent. So given March, we then pulled out from the data sets the average snow water equivalent in the depth across the elevation bands. The gauges are distributed across the elevation bands within the watershed. You can see the elevation bands in this upper graphic. We also pulled out the diurnal temperature series from the observed data at the gauges. Diurnal temperature series is basically needed to figure out melt, and it's min and max temperature range over a 24-hour period over the time period of your simulation. So we selected a 5-day period in March with the widest range. We also need parameters for lapse rate, melt rate, cold rate, and a temperature indice. Those we actually adopted from the previous study. They were provided into that study by the Cold Regions Lab of the Army Corps of Engineers. So the experts gave us that data, so we kept it. It proved to work well for us. So we developed our snowmelt inputs. I do need to mention that aspect was also really important. This lower graph is aspect, so north or south predominantly, because our 6 gauges, 3 of them face north, 3 of them face south, and you can see an observed difference in the amount of snow in those gauges. North facing is higher. So those are the snowmelt inputs. We built all of that into the HEC-HMS model, and we ran it. Then we needed to look at our RAS model to route valley flows. So we have our domain for the RAS model. As you can see here, we have 8 different sub-regions in that domain. 5 of them receive inflow from the upland basins, the hydrographic boundary conditions shown on this figure. 3 of them, the valley floor, receive rain-on-grid inputs. The mesh initially was a 200-foot grid, and then we added break lines to refine it at all the channels. So there's a break line in our model on every blue line you see on this figure, as well as ridges and roadways. One thing to note is that all of these regions have to be connected so that we can route flow from region to region and then out and ultimately out to Portola. Where a physical feature exists, that was the connection. If it was a roadway with a culvert or a bridge. But some of our basins did not have a physical feature for a connection. And on our initial model runs, we noticed that we had significant instabilities with simple connections in those locations. So our RAS modeling team devised a workaround, basically, of adopting dummy storage areas between 1 and 5 acre feet using an inflow point and a weir outflow, a weir at ground level, to do the flow transfer between those regions that didn't have a physical feature for connection. The workaround, or adopting that dummy storage area, you guys, worked really well. We went from instabilities and deltas of deltas in flow calculation of around 12,000 CFS, or a lot in the 100-year event, to down to 0.5 CFS. So the workaround we found to be very good for making our model work much better. We also, like I said, we did rain-on-grid on the valley floor. 68 hydrographs from those upland basins, because remember I said we had about 20 hydrographs that routed to each other before they met the edge of the valley. Here's a pro tip. Our RAS team did not have to hand enter those boundary conditions because holy moly, that would have been crazy. They used the DSS output from HMS, connected it into RAS, and basically were able to make that connection, connect those files for each frequency event and call it good. We of course back-checked everything, but that worked really well. One more thing I'll say is that both the full momentum equations and diffusion wave equations were tested across our entire study. The diffusion wave equation produced slightly better results during calibration, which we'll talk about in a minute. So that was applied all across our studies. We did also use an adaptive time step based on the Courant number and 20 iterations. Our team found that worked really well, balanced runtime and accuracy. So, we got our models all set up, but our goal was to really have a calibrated model. We really want to match up with observed flows at the Portola gauge on the Middle Fork Feather River. So all this gauge data, of course, gave us some calibration events, the floods of record. February 10th, 2017, 12,891 CFS at Portola on the Middle Fork Feather River. 4 to 12 inches total rain over 11 days across the gauges, 151 to 208% of February average snowpack. And then the max temp was above freezing for a few of those days. March 23, 2018, 6,108 CFS at Middle Fork Feather River Portola, 5 to 15 inches total rain over 16 days, 17 to 70% of March average snowpack, and max temp above freezing for 8 of those 16 days. So we pulled together these two events, and then we pulled together our observed data. One thing we had to do with the observed data is we had to figure out what the rainfall was and how to apply it. Two of our gauges, Grizzly Ridge and Sierraville, had accumulated 15-minute observations for rainfall. And they also had the same period of record. They were very consistent. So we selected those two gauges, one in the north half of the basin and the other in the south half of the watershed. We took the accumulated data over the observed storm, converted it to incremental data. Actually, we converted to incremental data before we even selected the storm. Then we pulled out the storm. You can see the storms pulled out kind of a bunch of leading days before our highest peak rainfall event, closest to the date of the observed peak flow. And then to figure out, we converted them to unit hyetographs. And then we needed to figure out, how do we split up this data across our uplands watersheds? So we did a little research. I looked around the internet and I thought about it, and NOAA has NEXRAD storm data. Had never used it before. It was actually pretty cool, but they have historical radar that shows storm tracks. So we found that the storm tracks, the typical storm tracks for these two events showed that rainfall kind of over the northern half of the basin was fairly consistent, west to northeast, and then over the southern part of the basin, also west to east. So we split along kind of this northern valley bottom line, applied the unit rain from Grizzly Ridge to the northern basins and Sierraville to the southern basins. Then we had to figure out how to apply the rest of the observed data. So to get the rainfall from the rest of our gauges, because the rest of our gauges did have observed daily max rainfall that we could use for the storms, we actually used Tyson polygons. I have to admit, haven't really used these in polygons in a long, long time. And I just said that word 2 different ways. Sorry about that. But GIS has a tool, does it for you. I agreed with the delineations. So we applied our 6 gauges with rain to the decent polygons, estimated total basin rainfall, and then developed basin-specific hyeta graphs. For snow water equivalent, snow depth, temperature, we use the same exact methods of applying that data that we used for the frequency event setup. We calculated the observed base flow for each of those storms, the floods, and applied that to the watersheds the same way we did for frequency events. And then we looked at our 2 reservoirs in the northern part of the watershed. We looked at both reservoirs had a gauge at the outlet. So we looked at the gauge data, and we noted that there's storage, but there's no outflow. So we set up our models for calibration to match that, no outflow. So then run the models, both of them, iterate. Again, we're looking to calibrate to the observed flow at Mill Fork Feather River at Portola. Based on this conversation, you guys see that most of our input parameters are from observed data, right? All of our snow information is from observed data. Temp is observed data. Rainfall is observed data. So that left us with basically one parameter to use for our calibration, and it was that constant infiltration. The land use and soil-based parameter that we basically, we estimated it based on reference information, but it was engineering judgment and estimating based on, kind of standard practice. So that was the one where we felt it was what we could use to calibrate our models. So we ran the 2017 event and the March 2018 event, and iterated between the HMS model and the RAS model, reducing that constant infiltration until we matched up within percentages that we felt were appropriate. Ultimately, we reduced the constant infiltration to 20% of the original value across the entire watershed, all of the basins. That's actually consistent with literature for review for winter conditions. Of course, infiltration is less when there's snowpack because the snow absorbs water. Also notably, in this particular watershed, again, in consultation with cold region, something I should have said earlier, we don't have frozen ground. That's an important thing because that, again, ties to constant infiltration, and frozen ground would actually lead to even less infiltration, but we were comfortable with that 20% of the original value. And you can see in these 2 tables at the bottom, our comparison of observed peak flow from our calibrated model to our gauge data, pretty dang close. Peak flows are 4.9 to 6.2% difference. That's pretty dang good. And then volumes, even better. March 2018 volume, we got to 1.2% difference. We consider that a win. We considered that calibrated. Our reviewers considered that a win and considered it calibrated. So we were super happy. So then we took those parameters, we dropped them back into our frequency events, ran our models, developed our frequency floods. And then everything got mapped. And I should have said, we did validate. We had photos from that January event and February events that showed that our depths and flood extents matched up pretty well. So we felt like numerically we were in good shape, and then we mapped it and we felt like we were in good shape based on extent from observation. So we're pretty happy with the results. Region 9 is pretty happy with our results. The communities are happy with the results. Right now, we're going through an update because right when we finished our study, USGS shared with FEMA that they had just flown some new topography in part of this valley bottom, and review indicated that it was sufficiently different in parts of the valley bottom, because the valley bottom is predominantly agriculture, sufficiently different that we should incorporate it. Region 9 did task us to do that. What they're looking at right now for what's next, separate from regular study processing, is that there has been a fire this year. In August, there was a fire over here, kind of in the eastern portion of the watershed. It did come over near Loyalton. Loyalton is right in this corner where all these labels are. Thankfully, did not cross into the town, but it did affect this portion of the watershed. So they are contemplating having us do a little bit of post-fire analysis in that area. So I really enjoyed this project. Like I said, it was the best data I've ever had to work with over my entire career. We were happy with our results. Region 9's happy with our results. I think that similar parametric analysis could be applied in Colorado. We have data. We have SNOTEL, but we also have climate data from Colorado State and observations for snow from the Colorado Avalanche Information Center. So we have some data too. So I think really one thing that AECOM is starting to look at in our work for Colorado Water Conservation Board is the impact of snowmelt in our watersheds, particularly on the west slope. So, and that's all I have for everyone. So if you have any questions, please let us know. Thank you for participating in my presentation today. I'm sorry I'm not seeing everyone's face just yet. And I thank you.